All right, we're going to go ahead and get started again. The first thing that we're going to do is give you a quick update with regards to the Pelican and G. That was one of the requests from the board last time, and we didn't obviously get it into this last session. But we do have a person from the SBU to come over here, tell us what the circumstances around Pelican and GeCAD are, and if you have any questions, please feel free to fire away. However, he does have a limited amount of time, and we want to move into threat modeling right after that. So with that, Philippe.
Thank you.
Thank you.
Okay, good morning. I'm Philippe Goetschel. I'm a product unit manager in the SBU, and I work primarily on antivirus. So what I'd like to do is give you a little bit of an overview of the acquisition of the GeCAD company in Romania, and then give you a little bit of background of why we do it, but would really prefer to spend most of the time on answering questions, if that's okay with you. Is there a particular area of interest that I should focus on, or we'll deal with that during the Q&A?
I think ongoing antivirus strategy would be interesting topic for us.
Okay. Good. So let me just give you kind of the brief overview. We announced on June 11th that we acquired the GeCAD company. It's a company that's based in Romania, in Bucharest. And what we acquired is the IP and the people. We're transferring a bunch of engineers over to Redmond. They should be arriving in the next weeks. The deal is not closed yet. It's contingent upon the approval of the Romanian Competition Council. The product line consists largely of multi-platform antivirus products. The ones that they have on the market today is most of their sales today are mail scanners that reside on the server, followed by a desktop product, followed by an online scanner. We bought the company for a number of reasons. First and foremost, we liked the IP. We liked the detection rates as measured by numerous third parties in that space, but also as measured by some of the lab tests we did internally. We also liked their people. We thought they would be a good fit with the Microsoft culture. Their English skills were very good, which is an issue when you acquire overseas. And the architecture made sense, and we found that it will be compatible with our other architectural efforts in SBU. We started the effort a little bit before Christmas. We looked at about 45 companies. We did a lot of testing of their products. We reduced the number down to 8. I visited about 8 in January and February. And then we had 2 finalists, and finally decided to go with the GeCAD company. Our product plans are really not finalized, right? And since we haven't closed the acquisition, we haven't been in a position to look at the code in great detail. We did a little bit of technical due diligence, but I don't have or nobody really here has a very thorough understanding of the quality of their code. We thought it was good enough to acquire, but we expect that there's going to have to be some rewrite.
Are you going to do security audit?
Well, the current thinking, and our product plans are not finalized at all, right? So the current thinking is whatever we ship, as soon as we've identified the shipping vehicle, we'll do security audits, just like we do with every other product. Sure.
Is there some idea in this that's embodied in this IP that is novel, that you can that's responsible for its success, or is it a question of using a bunch of things that are well known and having combined them in a really good way?
Well, as I said, we looked at third-party detection rate results, right? So because of the taint issue, we were not in a position to look at the details of how the technology worked, and we won't be able to until until they get here.
So there may be a cool idea under this, and there may not be, and you don't know it.
Yeah, that's right.
What was the difference in the detection rates that you saw from the various firms you visited?
They did very well on polymorphic, and they were good or better as the three big players in the detection of in the wild viruses, and the big three being CA, Trend Micro, Symantec, and NAI. Not in that order, but that's something like that. Oh, Symantec?
No, I mean, I just don't know what detection rates talk
Oh, in the wild, the industry.
10% or?
No, in the wild, detection rates are upwards of 99, and then polymorphic is between 60 and 90%.
So they have more than a scanner then. They must have some heuristic engine that's looking for variance.
Yeah, yeah, they have. As part of the engine, they have a heuristics engine. They have about, they have a number of small mini engines, each one specialized to look at specific file types. Yeah. The other acquisition we did in February, which was a little smaller, was the acquisition of Pelican, and that resulted also. It's a similar deal. We acquired the IP and brought over a few engineers from Tel Aviv, and that was not a shipping product. That was a company where we just acquired the IP and the knowledge of the engineers that built the IP. It's in the behavioral blocking space. I'm not intimately familiar with the technology because it doesn't report into my group.
Could you say that again? What was
The name of the company?
No, the focus is on what?
Oh, behavioral blocking. They had a product in the marketplace, and then they took it off the market, and we bought the company.
So behavioral blocking is like a reference monitor that sees what's happening, and so then certain things.
Exactly. It's a bunch of behavioral rules, like Notepad can't send email, and these rules can be set by the administrator or by a central authority, depending on whether you're targeting the consumer or the corporate user. I'd love to.
So looking forward, Philippe, there's a lot of possibilities, right? You could combine these two products and go out to the TV market. How does Symantec and Trend and CA, what's their reaction to this? I understand you had an antivirus meeting last week.
Yeah. A couple of things, right? I think most of the press coverage and the reaction from partners was neutral to positive. What we're really interested in mostly is to keep the existing antivirus infrastructure and ecosystem in place. So what we've said publicly is that if we're going to build this into our products, the signature portion will always be fee-based, so we will charge for that. Why? Because we are interested in keeping the existing players or keeping the ecosystem in place, because we think competition in the antivirus space will ultimately benefit the consumer, because more competition will keep the detection rates high and will assure that malicious code will be fought from different angles. So we're doing a bunch of things to create a platform to support our effort, but also third-party effort. Most of the major products have APIs that we have been publishing and will be publishing moving forward. That includes the Exchange VS API. Office had a macro initiative since '95. They have a bunch of APIs for all their applications. That basically consists in ways to hook these applications at the file level.
The idea there is to make it easier for
AV vendors to hook
into your operations.
To hook by your operations. That's for file-based. And then for non-file-based, like Messenger and SharePoint servers, we have APIs that allows third-party vendors to hook just data streams. We also put in a lot of energy over the last 2 or 3 years to unify our file filter manager. You need to know that until now, or until the Longhorn time frame, because of memory constraints, you can only run a max of 1 or 2 competitive products at the same time. And the file filter manager frees up that space, increases reliability of antivirus engines, and will allow you to run several engines at the same time. Antivirus has been, for the last 4 years, probably one of the biggest contributors to crashes of the operating system. So this more reliable architecture will definitely help improve that, we hope. Yeah?
Does this company from Romania also produce software to detect spyware software, or
No.
and there is no plan of acquiring software in that?
Yeah, the question is, what are we doing in the spyware space?
Yeah.
Right? So what we have is, we have an anti-spam group that sits in MSN
Spyware.
that is not directly related to what we are doing, and most of what it's actually an MSR project that recently got moved into MSN, and anti-spam today resides in MSN Mail. It's going to go into Hotmail, and it is or is going to be an exchange. Spyware is not something we've looked into yet. I've had some preliminary thoughts on it. There's a lot of legal issues on what we can do against spyware, and the legal environment in some European countries and in the U.S. are vastly different. So it's definitely on my radar, but I'm not prepared to give you any thoughts that sound consistent or even intelligent on this one. Yeah. Good. So hopefully next time we'll meet, once we have the bits in-house, I'll be able to give you a little more insights on the technology. Steve, anything else?
I mean, it's really for the board. So if they're happy,
Are you getting any grief?
they're happy. You've gotten off easier than I did.
Getting any grief with the lawyers in incorporating things like the virus scan?
We're getting advice from our lawyers, which often translates into grief. You're right. It's a challenge for us to put that into our products, because even when we announced this deal, a lot of people compared what we might do with AV to the Netscape situation.
Yeah.
So there's a lot of aspects of that, and what we need to do, kind of as a high-level guidelines, whatever we do with signatures cannot be given away as part of the operating system. We'll have to make that available on a standalone basis. So for a product like Exchange or an integrated product that might include several components of that type, the signature will always have to be made available separately, and we will probably make it available through Windows Update 4 fee. Yeah. Yeah.
So one of the risks of having a single shared infrastructure, it's good. I guess there's some argument it's good for competition and so on, but it also will inhibit some kinds of intellectual developments, because the existing infrastructure defines a framework, and there are going to be some approaches that really don't play well with that framework. The framework imposes a set of decisions on designers, and maybe the next great AV product would leverage not having to play that way. So what do you do to increase the chances that you're not imposing decisions that are unnecessary and therefore are going to preempt new approaches?
Yeah. Well, a couple of thoughts. It's always hard to predict, when you set up an architecture, what are intellectual frameworks that don't fit the architecture because they're novel and are outside of that. So most of our thoughts are API based. It's largely our current thinking is based on letting the guiding principles are letting AV packages access files either at the file system level or at the application level, or or where applicable access data streams. So data streams would be more like messenger oriented or SQL oriented, or to some extent even exchange oriented on the store. And that's where we're focusing on. I think this approach still leaves a lot of room for innovation in how to come up with new heuristics approaches. But I'm not sure if we systematically thought about what other ways there would be to fight viruses. Viruses is not a state-of-the-art technology. It's something fairly mature. It's well understood, and a lot of the innovation. There's some tactical innovation in viruses, but a lot of the innovation is more in the IDS, BB space than in classical virus research. Did that answer the question?
And then the one issue I can think of, if you do normalize or standardize the technique for AV vendors to hook into your OS, you've also given me a single point of failure to attack. Because if I can disable that, the API level, I can disable every single antivirus product because they all use the same method to hook into the OS.
Yeah.
I only have one attack point to try to bypass.
We're looking into ways to make by now the single biggest point of failure, as I pointed out, is a virus can disable the engine altogether or disable a user setting to run the engine. So from an antitrust point of view, the engine has to be, the user has to be able to have the option to install or not to install the engine. Right? Well, if you have that facility inside your code, a virus can do the same. So then, you have legal constraints versus security requirements. And so those are some of the things we're struggling with. Yeah.
So something that a little bit more general here is, as we build in defenses that either block behavior or look for behavior that we don't want, and this covers several of these, that has the potential to keep developers from designing architectures that are resistant to that kind of behavior.
Mm-hmm.
And in the long run, building resistance in, which is not something that Microsoft has done well over time, might be a better approach and would also help address some of these issues of single point of failure or getting yourself thinking along a line that this was going to protect us. So getting away from self-modification, getting away from carrying macros in with data files is actually likely to be a better solution than developing something that monitors for that. And so this is not to criticize the acquisition, but to make the point, it shouldn't be used in place of forward thinking to avoid that kind of construction.
I think starting with AV is a very reactive technology, right? I mean, by definition, just like in medicine, it's reacting to something. And I think with my statement earlier that a lot of the innovation is in these newer spaces, I think it's an effort to try to get off the curve and look at this more systematically. But I think it's going to take a long time to get there.
Well, if you're going to compare to medicine, one of the problems now is that we put a huge amount of research dollars into coming up with basically curative or palliative measures after the fact instead of in the vaccination and fixing the health practices that keep people from getting sick in the first place. And I would much rather not get ill rather than be treated after getting ill. And I think the same kind of philosophy should be applied to the software production, which is find what those characteristics are that enable this kind of behavior, because it not only enables virus activity, worms, Trojan horses, spyware, break-ins, and otherwise, rather than getting into a mindset. I'm not suggesting you're going to do this, but it's tempting that you have something that will find these problems as they occur.
Yeah. I think one thought that you triggered with your statement is, unlike vaccines, maybe we should look at and overhaul our health processes, right? And the equivalent, or one of the equivalents in the computer world, might be the area of vulnerability assessment. Right? So we're working on that. We have a couple of products out. I think there's MBSA, the Microsoft-based system analyzer. There's going to be some of these components in the security center that analyzes the health of your PC on an ongoing basis. But again, it's after the fact. It's more a process that looks at several checkpoints on your machine and looks at if you're logged on as an administrator, do you have the latest patches. So I think we're just at the beginning of a huge iceberg. We're just touching the surface, and we are not systematically thinking yet about how to get ahead of the curve. I would say 90% of our efforts today are reactive, and we'd love to work with you on proactive approaches.
Okay, any more questions? All right, thank you very much.
Thank you.
And with that, we will go into our discussion of threat modeling. I'd like to introduce Frank Swiderski, and he will take the first portion of the discussion and keep it interactive, and then Mike Howard's in the back, and he will chime in where appropriate and on the appropriate pieces of his talk. So with that, Frank.
So the threat modeling talk, actually, can we switch? Not it? Is it?
Oh, you want one? We're trying to bring that up.
Yeah.
There we go.
Of course, now I can't see it. Cool. Okay, this talk that I'm going to give on threat modeling is a talk that I gave recently to the Department of Defense. It's also the basis for some training that we'll be giving later on in August, I believe, actually. So it will be included in some of the developer training that we're giving to people here at Microsoft. And it's based on a lot of work that we've done in the area of threat modeling, inputs from, obviously, Michael Howard, from research from various outside vendors and other experience from people throughout the company. So that's the basis of it. Background for myself, I work over in the Secure Windows Initiative attack team. We do a lot of penetration testing and threat modeling and things like that. So this is kind of part of my responsibility is threat modeling. So first thing I want to go over is what do we define threat modeling to be? And really it's a process that helps us understand and document security threats. One of the things that we're trying to make threat modeling is we're trying to make it a lot more methodical and complete than it has been in the past. We've seen a lot of teams that do very effective threat modeling, and we've seen their products, the security of their products increase dramatically because of it. But we've seen other groups that have had a little bit of difficulty. So we're trying to improve that and make it a lot more methodical and complete. Threat modeling also describes a system's threat profile, which I'll discuss in a minute. It helps you describe the security of a system, characterize it, say how secure, relatively secure is this product, and it may find vulnerabilities. Often does find vulnerabilities, but finding vulnerabilities is not necessarily just the only point of doing threat modeling. So some key concepts. Threat model describes a system's threat profile. A threat profile is defined as all the things that an attacker or an adversary to the system might try to do. So a threat is not a vulnerability, the second key point that kind of relates to that. A vulnerability is something that an attacker can actually do to the system to exploit some vulnerability to gain elevation of privilege, cause a denial of service, or what have you. A threat is simply what they might try to do. So you can think of a threat profile as a sort of a documentation of all the problems that you're trying to solve by adding security to a product. So the point is not just to find these vulnerabilities, it's also to define the threat profile. If we define the threat profile, then we can go and we can say, based on all these threats that we've come up against the system, we were mitigated against 90% of those. So we can give a somewhat quantifiable number, or we can give a number to how secure we think that the system is when we deploy it. And a system is just defined as anything that exposes functionality to an end user. We do threat modeling at different levels, so we'll do threat modeling at like the feature level of some application, but we'll also do it at the application level. So when you're doing it at the feature level, the system is defined as just that feature. So system is just kind of a generic term that we use to describe whatever it is that we're threat modeling. So we have a relatively simple diagram of the threat modeling process. The first thing that we want to do is collect background information about the system. Then we want to model it and finally determine threats. So we'll start with collecting background information. Background information is important because it helps us bound the threat model. So it helps us contain the discussion so that we don't go off on tangents that are less relevant to the system that we're actually doing threat modeling on. It gathers information about dependencies that are security critical. In most cases, the system that you're threat modeling is going to have dependencies on other systems. That if those dependencies were to break, the security of the system you're modeling could be compromised. So this is where we collect that sort of information. And it provides necessary information for people to understand the threat model. Obviously, like I said, this gives us the background information that we need in order to complete the threat model.
Can I ask a question?
Yes.
Does that mean how people have tried to attack it in the past, or does it mean asking the people where the vulnerabilities are?
Not at this point, no. As far as historical threats and attacks, that's something that we do during the modeling of the system.
So when you give the background information, this is something where you're talking to the developers and asking them what they think the weaknesses are?
So as far as the background information, this is something, when we do threat modeling, we will typically have involvement from some security-related people, developers, program managers, and testers that are involved in the product. So it's not so much us going in and saying, okay, we're going to model your system. It's us as a group going through the process. So background information, I'm going to go through each one of these, so I think hopefully it'll be a little bit more clear, but if not, just feel free to ask. So the first thing we want to do is gather use scenarios. Use scenarios describe how a system is intended to be used or not intended to be used. So for example, you could say that if the system is deployed in this configuration, we're not going to be mitigated against all these threats because it's this unsupported insecure configuration. So it might be some sort of a legacy configuration, for example, that exists to support background or backward compatibility. Basically, this helps us define what we consider a secure configuration, what we consider an insecure configuration that could impact the threat model. I'm going to skip ahead. The examples that I'm going to be giving are for this fictitious telephone made by the Fabricam company. Basically what it is it's just a telephone with an answering machine with a few additional features like access control. where you have to enter in a password to be able to call, make telephone calls or make long-distance calls and things like that. So it's completely fictitious, a little bit abstracted from the software world, but we use it to kind of describe the concepts. So I'll be giving examples from that. The first one that I want to give here is for the use scenarios. You can see that the first example I have there is that the phone is going to be connected to the PSTN, and the security of that network is beyond the control of the phone, right? So when you use a phone, you have to plug it into the telephone network, and we have to assume that that network is insecure, and there's nothing that we can do about it because that's obviously provided by some telephone company. So that's beyond the scope of our threat model here. Second one there is that the phone is designed, in theory, to be deployed in like a conference room where people could be walking in and out. The idea here is that if it's deployed in some location where people can use it, you'd probably want to enable access control so that random people, maybe your cleaning crew or something like that, can't come in and call long distance or overseas. So I think we've mostly covered the use scenarios relevance. This talk is actually usually takes several hours, so some of these slides I'm going to kind of go quickly through. But the important thing here is that use scenarios really do help bound the discussion for the threat model. In addition, they can be used in some cases as mitigation for threats. So you might imagine that there's a threat against the system, but it's only a valid threat if it's deployed in an insecure configuration. So we could say that because that's unsupported, and we've documented that it's unsupported, that threat is mitigated.
For what it's worth, I've actually found from experience about 50% of threat modeling meetings tend to rat hole on something that's got nothing to do with the system whatsoever. And by bounding it really early on, you can just nip that in the bud and just stay focused. So it's really important to bound it with these usage scenarios.
I have a question.
Yes.
Is it okay to ask questions?
Yes, by all means.
Okay.
Yes.
So you've invented your own methodology for these user scenarios. Why not adopt UML, which was invented years and years and years ago, has standards committees, lots of documentation, everybody else in the industry uses it?
Sure.
I didn't mean to make that sound adversarial. I apologize.
No.
Stands.
To be honest with you, as far as the methodology here, this wasn't done in a complete vacuum. It is based on some other work. Obviously not that, but for example, this process is very similar to failure modes and effects analysis. So it is based in other. It has some basis in other standards that have been around. So as far as why did we choose not that, this. Seems to work, and one of the reasons why we have our own methodology here is that what we're trying to do really is model the adversary, and the adversary has a very data flow driven view of the application. If I'm attacking some web server or any network based server or something like that, the only way that I can actually attack is if I can somehow supply it with data or make some RPC as an example. So what we're trying to model here is more of the adversary's view of the application and the inputs that they have into the system. So what we've come up with our process so far, we feel works relatively well. Obviously, we're open to suggestions as far as modifying it, changing it, including other methodologies, but. We find that a lot of teams have been able to take this methodology to quite a degree of success. So it's put simply, this has worked for us.
Are the usage scenarios English level descriptions, so that they're not really precise specs?
Right. They are English descriptions. In fact, the majority of the information that we collect here are English descriptions, and part of the reason is that while we want to make this formalized, we want to make it complete. we always have to have a trade-off between how formalized it's going to be versus how effective it's going to be given the time that we have to do it. And I think that going this route has worked pretty well. Yeah.
So you said that we're using this data modeling approach, data supply data, or procedure calls. Am I to take it from that then that the range of threats doesn't include somebody with physical access who's interrupting power or observing signals, or you're really looking at a network-centric attack? Is that it?
That for the network example, sure. But so a good example of that, of exactly what you're saying is that this fictitious phone that we're talking about, obviously. Somebody could come in, unscrew the cap to it, and plug in a listening device or something like that. That is something that we would say okay, that's an unsupported. I mean, if you have it, sorry, go ahead. You want to add?
I was going to point out, Frank did distinguish between threat modeling at the feature and application level, and threat modeling more at the whole system level. So, for example, when MSN applies the approaches like this to one of their web services, that's when they naturally take all the physical access, all the human factors, things into account, the human-based attacks, and we do encourage people to consider whether those are relevant for their particular scenarios. At the level of a software component, it's basically enough to identify that, somebody who has administrator access can do X, and externalize the whole question about how unauthorized people can get that access, which would include the physical abilities.
In fact, previous to working in SWI, was over in the Common Language Runtime, which is the foundation for the .NET framework, and we use this process for individual base class libraries. As an example, you can imagine that things like the .NET framework as well as Java have issues in that they're intended to allow code to run in a sandbox. So for any class library that's exposed that may be running at a higher trust level than the caller to that code, there are certain threats that exist. So it doesn't necessarily have to be a network-centric application that you're modeling. We use this to, again, quite a degree of success with some of the threat modeling of base class libraries. So.
I was thinking specifically of smart cards, for instance.
Sure. Yeah, it's the example. Most of the examples that I will give are, to be honest with you, are network-centric, or in some cases class library-centric, because that's where my background is. But in theory, you can apply the methodology to a lot of different things, and that's one of the reasons why we use the phone as an example. Yeah, we've found that it works relatively well. It's really up to the people who are using the methodology to apply it to their area. So, but yeah.
Just for my understanding, is a threat something that you can physically see as an activity which you can consider as a threat, or could it be a whole sequence of little innocuous-looking activities, maybe scattered over time, which cumulatively lead you in a vulnerable state? Would that also be a threat?
So threats, yes. I mean, the answer is that threats can be a lot of different things over the course of time, and obviously threats that are aggregated can lead to a much more severe vulnerability. Should each of those threats be realized as a vulnerability, the combination of those could lead to a much more severe vulnerability than any one of those threats by itself. Yes, but
the little entities I did not mean as threats. By the individual discrete entities are meant by actions which were not necessarily perceived as threats, but cumulatively added up either to be a threat or to result in a state.
Can you give an example?
Lots of cases where let's say you bring in some data structure which puts you in a certain state,
sure,
which is not an acceptable state, but it's not sufficiently disruptive to be viewed as a perturbation. But collectively, they reduce the sensitivity of the system.
I would argue that should be a threat. If you're putting the system, if you're priming the system, if you will, with by putting it into a certain state that you can then use to build a much more complicated exploit, then certainly I would view that as a threat, to be honest with you.
So if 1,000 little activities lead to a cumulative threat, what goes with the 1,000 little threats you have to think about?
Sure. I mean, you can certainly enter each of those as a threat. You could also take the, if you're depends again, it depends on what you're doing the threat model, what level you're doing the threat model at. If you're doing it at a much higher level, then you can say that to realize this, you could use the whole sequence as your single threat, and then you can say to realize this threat, the following conditions have to be true. So it depends on what level you're doing it at. But typically, because we do threat models at different levels, down at like the feature level as well as the application level, the little micro threats are covered at the lower levels, so at the feature level, and those bubble up to larger threats at the system level.
How does that work with your earlier assertion of both methodological and complete? Complete, I would argue against in this case. I can create a pathological sequence which could be infinite and then say, and maybe scattered over time and stuff, it's going to add up to a threat. Would completeness then be a facet that you could actually argue for?
Yes, again, because like I said, I would argue that those individual steps that have to occur, those are threats at the feature level typically, and so you will see those, and those will be threats in the feature level threat models. Yes.
Have you found many vulnerabilities for which there was no threat in your analysis?
So that's one of the things that we're trying to cover with this with the way that we're doing threat modeling moving forward is that we have enumerated these threats, and so should a vulnerability be found later, since we've got the threat profile documented in the threat model, we can go back and we can say, is there a corresponding threat for this vulnerability? If there is not, then we use that to feedback and try and figure out what was wrong with our analysis in the first place. So occasionally, yes, we do find vulnerabilities that did not have a threat associated with them, and we go back and the idea is to go back and figure out what went wrong.
Can you give us an example of a vulnerability which has no threat?
No. There are examples, but I don't. Having not been prepped with as far as what I can share, I'd rather not, to be honest with you.
Okay.
But
you make a distinction between threats and vulnerabilities, so there must be some vulnerabilities for which you found.
Well, a good example is this: if some external researcher finds a vulnerability in one of our products, chances are we didn't have a threat associated with that, because we are changing our process such that when we find threats that manifest themselves as vulnerabilities, those should be fixed going out the door. Now, if somebody finds something external, we have to go back and we have to figure out what we did wrong. Sorry.
So it sounds like from the point of view of your process, internal process, there is no distinction because you handle everything you find.
Between,
threats and vulnerabilities?
No, there is. A threat, again, like I said, a threat is an idea of what an adversary might try to do to a system. A vulnerability is a manifestation of that threat. So a vulnerability is simply a way of exploiting a threat. Does that make sense?
Yeah, it makes to me.
Really?
Okay, so...
Hold on a second.
Okay.
Folks, this is a chairman assertion. It's going to be tempting for us to try to reform the terminology let me finish. That Microsoft is using in light of existing terminology which has slightly different meanings. I think we should resist that temptation because we're not going to get through the whole talk and just try to go along with this terminology, and only when you can't understand what this point the speaker is trying to make, start probing for that kind of question. Because there's a big picture here that we need to see, and we're not going to see it if we really drill down on slide 3 to what the difference between a threat and a vulnerability is. Now, I understand there may be some real flaws in this business, and we need to drill down, but try to be a bit careful about it. Well, the intention is not not to point out any problems with the approach. The intention is to really understand what we mean by the difference, because there was a slide on the previous slide, there was a difference between threats and vulnerabilities. It's not clear to me that there was a definition attached to the difference. So all I wanted to do is to find a reasonable definition to understand what is it that we are trying to do here.
So
my concern is more general.
I suggest we let the speaker continue so that we get the start of the entire process, and then we if we have time, we can try to help him formalize it. But we're not going to do that in real time.
Yeah, just one final comment on that. Think of a threat as a goal, an attack goal. It's just something that an attacker wants to do. A vulnerability is a way that he can actually accomplish that. So you have mitigations against a certain threat. But we'll discuss that later when we actually get to the threat enumeration and vulnerability discussion. The next thing I want to talk about is external dependencies. Like I said, a lot of systems are interconnected, be they at the feature level or at the application level. Systems are interconnected, and because of that, a lot of times you have external dependencies. A good example, the example that I always give on this one is that for example, if you've got a web server that has access control that can be applied to individual web pages, a lot of times that access control is based on the path from the virtual root, if you will, for that web page. When it's important because that web server relies on the underlying file system when it actually goes to open up that web page and serve it to the end user. In this case, it's important that whatever normalization that they do to the file name that's passed in by the web client, that normalization matches whatever normalization is going to go on in the underlying file system. So in that case, the web server would have an external dependency on the file system normalization of the host operating system. In that if the two are inconsistent, then you might end up with a case where the access control at the web server level says, okay, it's fine to open up this, or sorry, we think this is a file that's okay to open, but when it's normalized by the file system, it might be normalized differently. Obviously, there have been vulnerabilities associated with that in the past. Simple things like all sorts of different things as far as IIS and NT have been concerned, like alternate data streams and things like that. Because the file system used to parse things slightly differently. Yes?
I don't expect that you include every possible external dependency. For example, I imagine that you don't list every time that the compiler has to work as you expect, for example, and things like that, right? So, are you finding that you're listing the important ones? How do you know if you're getting the ones that actually matter?
So that is actually a good question, and one of the ways that we try and describe that is by describing the interconnects between the system and externals, and that's one of the things that we use data flow diagramming to show is how whatever we're modeling fits into the bigger picture, so we can see what dependencies they have there.
So it's always that there's a consistent level of abstraction. You never look at the infrastructure below. You look at applications talking to one another, for example. But
right.
Yeah, okay.
So I'm going to skip over this example because I gave the web server example. Again, I want to get through this. External dependencies, again, the main relevance here is that because systems are interconnected, I may have a dependency on some other system. If that dependency breaks, it's going to impact the security of my system. So that's really the main reason why external dependencies are important. The next topic we'll cover really quickly. It's implementation assumptions, and this is really a placeholder because we'd like to start the threat modeling process at the same time as specification. The reason why is a lot of the information that we collect during threat modeling is the same sort of information that we collect during specification time. So an implementation assumption is simply a placeholder where we say that, okay, well, we've identified some issues, and we need to make sure that when we implement it, it's implemented in this certain way. So all it is it's a placeholder for implementers to make sure that they implement it in a certain way. So there's various examples that I'm not going to cover right now. External security notes is the next thing. An external security note is basically the analog to external dependencies. So it's the place in your threat model where you might publish, for example, if I'm the underlying OS, this is where I might publish how file names are normalized. So this is, again, like I said, the analog to the external dependencies. This is where somebody who has an external dependency on your system would go and verify that that external dependency is correct. So this information can either be published proactively or reactively based on somebody's dependency. And finally, the last bit of background information is called internal security notes. Mostly what this is used for is for cases where either a business requirement or some other non-security requirement has some impact in security. So for example, this is where we might describe some legacy behavior that we still have to support that may have an impact on our threat model. So this information is really just to document maybe trade-offs that are made in certain configurations for reasons that are not security related. The example that I give here is that this phone uses volatile RAM to store various information instead of non-volatile RAM with a battery backup, and the idea being that it was cheaper to go with the battery and the volatile RAM than it was to go with the non-volatile RAM. Obviously, that's a trade-off security-wise, because if somebody was able to remove power from the phone, then you could lose all your information. Versus if it was non-volatile, you would not have. That's a threat that you would not have. So again, really the relevance here is for somebody who this is typically not information that's public information. This is something that somebody who's reading the threat model would need to understand to help them understand some trade-offs that were made. The next thing I want to go into is the modeling of the system. So this is where we actually get into the actual data flows and understanding what the adversary's view of the system are, or what it is. The first thing that we want to cover are the entry points. Entry points, like the first bullet says, they define the boundary of the system being modeled. These are all they're basically all the attack points for a system. So for example, with a web server, you might have, depending on the level that you're doing your threat model, and I will give an example later of how entry points can be layered, but you would have, for example, port 80 might be an entry point, port 443 might be an entry point. But entry points basically, if you're describing the system at a context level and data flow diagram, entry points are anywhere that you have this, the system is a circle, and then you have external interactors as rectangles or data stores. It's basically any place that you have an arrow going to or from that circle and some external entity. Yes?
So what about the fact that let's think of a very simple system, which is a single thread, single process, a single thread. Do you consider the fact that the processor is being multiplexed and it requires the processor as a resource to be an interesting part of the boundary? I picked that because it's entirely implicit in when you drew that diagram on the blackboard, you didn't bother to write the processor down.
Sure. So it really depends on what you're modeling, to be honest with you. And I'm not sure I fully understand the question as far as relevance to entry points. But
well, let's say that context switch code is
sure
an entry point, but it's a very implicit one that can be fired at any control point.
Sure.
So presumably it's beyond the level of detail of most models.
It also, pardon me.
So you might wonder why I care. Well, I'm building a web server and I'm worried about denial of service attacks.
Sure.
Denial of service attacks work at the level of the process schedule.
So that is not really an entry point per se. Entry point is basically where the adversary can attack the application. So, and the adversary is not attacking it via the processor or via the context suite.
On which the application is dependent doesn't count as attacking the application.
Or it's not an entry point.
Yeah. So that's the processor. Really, is more of a protected resource or an asset, and that's something that we'll cover shortly. It's not really an entry point. The entry point is how am I attacking the application, and it may be if you're an email client, then it may be by sending a malicious email. If you're a web server, it's by sending sending a request to port 80 or to a specific page or something like that. The entry point is basically how an attacker can get into the system. So it defines the boundary there. The resource really there is the processor when you're talking about denial of service, via resource starvation. So the processor and memory and things like that, disk space are all protected resources or assets.
And I guess that would be an external dependency. So the processor may not be.
I would argue it's more of an asset in that than it is so much of an external dependency. So.
Do you have any thoughts or experience with tools to validate that you got all the entry points? You could imagine having tools that look at the code and see what the entry points look like.
So that actually, John is unfortunately gone for right now, but that is something that we're having discussions around as far as like what can we automate, and that is something that John is involved in. And
maybe we'll come back to that later.
Yeah.
So what about the fact that this entry point should not be circumvented by an attacker? For example, we have exposed APIs. Suppose that some code transfers at arbitrary entry points and not used.
I'm sorry.
Suppose that some code transfers to arbitrary instructions as opposed to going through the APIs. In other words, how do you ensure that these entry points that you identified are not circumventable?
Well, it's mostly the entry points are intended to describe any interaction between the system and externals, be they the host OS, be they some RPC interface, be they if we're talking class libraries, maybe it's the method calls that you can make. I mean, they're relatively. I think for any given system, they're relatively well defined. Especially if you go with the example of a class library. I can't circumvent. There isn't really any way for me to attack a class library short of going through the methods and properties that are exposed. So if I've defined those, or obviously if it consumes information from the disk, or if there's some other it basically I think is relatively well defined for any system that you're doing a threat model on. So I don't really understand how you could miss an entry point.
Well, some of these attackers really use machine language and assembly language for control.
Exactly, and they supply that via some entry point.
Some of them are not so well behaved.
I'll give you an example from the Java world, if I may, which with your class library thing. It's a bit of a long example. In Java, there's this thing of inner classes that you guys don't have, fortunately. It gets messy. In the Java bytecode language, on the other hand, they don't have inner classes. So when they compile inner classes, the inner class gets put side by side with the outer class, and accessor methods get added, so the inner class can still get to the private components of the former outer class. That's a new entry point that is not visible at the source level. And it's a way, potentially, of getting around the interface.
Right, but that's still an entry point.
But if you just look at the code,
but
you
it
wouldn't
can
see
be an
it.
arbitrary one.
Well, right, but presumably if you're doing a threat model of this system, then you understand that if this were to if that were to occur, then it adds these additional entry points.
That's what you would hope, yeah.
So I mean, yeah, I mean, if you static analysis of the code is going to give you certain entry points, but if you're doing a threat model and you don't understand that these additional entry points may be added because of the way that you're using it, then you're probably not the right person to be doing a threat model.
Actually, can I just make a comment? I think I'll hopefully save this from going further in the rat hole. It's quite seriously the model. If you're modeling a Java VM, they would be absolutely taken as entry points. I think if you're modeling an application that say used Java applets, you see the Java, the sandbox and stuff as a kind of a black box. The entry point would be how you got that code on the box. The different levels of looking at the entry points. I think if Frank and his dev, when he was in the developer division, may have actually worried about some of those really low level entry points, but now in the role that he's in now, we look at things at a slightly higher level of abstraction at an application level. We look at different entry points altogether, but they're absolutely valid entry points, just a different level in the tree, in the layer.
Okay, I'm going to go ahead and move forward beyond the entry points. The next thing that we're going to discuss is our assets, and this is where we'll talk about things that, like the processor. Assets, and this is something that Michael Howard and I kind of have some slightly different views on. But assets can be concrete or abstract, and they're basically threat targets. So they're things that they may be. You can also call them threat targets. You can also call them protected resources. They're things that an attacker is trying to get at. So, for example, in the case of a denial of service, some of the protected resources there might be the processor, the memory, available disk space, things like that. Things that an attacker can attack in order for the system to the availability to be affected. Other examples that I give, the example there is an example of a peer-to-peer application. You've got a peer-to-peer application. One of the assets for that application is network coherency. It's not necessarily something that's really concrete. It's a little bit more abstract. Obviously, if I can affect network coherency by breaking the network into a bunch of disjoint graphs, then node A over here is not necessarily going to be able to talk to node B over here anymore. So I've affected a denial of service. So somebody who's attacking a peer-to-peer network, they might be attacking the network coherency. Other examples of more concrete assets might be like the corporate data that's stored in a database. If somebody gets a hold of this corporate data, that's information disclosure, right? So examples of some things for the phone. I have like the speed dial list, that contains names and numbers that may be sensitive, especially if the phone is deployed in a multi-user environment. Caller ID, access to the telephone network, is a somewhat transitive protected resource in that the phone is acting as a gateway to the telephone network, and it has certain access control that should prevent arbitrary users from accessing that. Other things like long-distance calling, obviously, phone configuration. If somebody were to change the configuration of the phone, then that would be bad. So assets. One of the important things to know about, or to note about assets, or the way we consider assets, is that you can't have a threat without an asset, and vice versa. Really, you can't. If an asset doesn't have a threat, then it's not particularly relevant to the threat model. But for any given threat, there's always an asset that's being attacked. Again, because, like I said, they are defined as the targets, the threat targets. So it is possible to have multiple assets apply to a single threat. So a threat could affect multiple assets at a time. But you have to have at least one asset for any given threat.
Does an asset have to have value?
It's implied that it does have value because it's something that you're trying to protect, right? So it may not have readily visible value, but it certainly has value. If it doesn't have value, then there's no reason to protect it against an adversary, right? So it has implicit value, and obviously it may also have explicit value. Like I would say that network coherency is somewhat implicit, has implicit value versus corporate data, which has very explicit value. Trust levels. The next thing I want to cover is trust levels can be applied to both assets and to entry points. And basically what it is it's a characterization of, in the case where it's an entry point, it's a characterization of what you can tell definitively about somebody accessing that entry point. A lot of cases, especially like when you're talking about a .NET application that's running in the web browser, there isn't a whole lot that you can say about that. You can say that it's that application may be coming from some unknown anonymous remote user. Same goes for if you're modeling a web server and you're talking about port 80. Assuming that's deployed on the internet, then somebody who's accessing port 80 is probably going to be remote, and they're also probably going to be anonymous. So it doesn't necessarily correspond to things like NT groups. It basically tells you, it basically describes anything that you can definitively tell about somebody, some external that's interfacing with that entry point. And we use this to prioritize our discussion. Obviously, an entry point that any arbitrary user or external can interface with is probably going to be a higher priority than something that we can say for sure requires local file system access, as an example, because there are more preconditions in order to access that entry point versus the one that can be accessed remotely and anonymously. For assets, trust levels define who should be able to normally affect that asset. So, for example, network coherency in the peer-to-peer application, you could assume that if there are some administrative nodes or something like that, then it's probably legal for those administrative nodes to be able to affect network coherency versus some user node should not be able to. So it basically just describes who should be able to access these assets. But again, like I said, they aren't specific to any particular technology like NT. They aren't NT groups, as an example. They're specific to the system that you're being modeled and what you can definitively tell about the external users. So again, like I said, trust levels that have more preconditions are typically lower risk. They're not always, but they are typically lower risk. If I'm an attacker attacking a system, I'm going to first try and attack the interfaces that I can get to anonymously, because if I have to authenticate first, then that number one, in theory, cuts down on the number of adversaries that would have that authentication information can get to that interface. So it's a little bit less risky. So we use this just mainly to prioritize, not so much to cut things out of the threat model, mostly just to prioritize. So these are just some examples for the phone that I'm going to hop through. The next thing we're going to talk about is data flow diagramming. We use data flow diagramming, again, because our approach is kind of data-driven. Like I said, it's really based on the premise that an attacker can't attack a system unless they can either supply it with data or interface it in some manner. Via an API call, whether it's directly via a class library or remotely via RPC or something like that. But in any case, in any event, you are interacting with the system. You are supplying it with data. So that's why we've used data flow diagramming. It also has other benefits. And I took this out of writing secure code. Thanks, Mike. But it also has benefits in that you can drill down into areas of concern relatively easily by taking any single processing node and saying we're interested in what goes on in that and blowing that up into a lower level diagram. So you don't have to model the entire system to the same level. You can model only the most security relevant things to the lower levels. So it fits relatively well. So data flow diagramming, you guys are, I would imagine, relatively familiar with this, so I'm going to skip past that. So for the telephone, basically at the context level, it also kind of fits in really well, because at the context level you have your system models as a circle, and anywhere that some external interactor has an arrow going to or from it, that's where an entry point is. So you've already defined those entry points, so in theory this fits in relatively well at that level. A few things that we've kind of added to data flow diagramming that we find somewhat useful a lot of times, especially when you're talking about things like base class libraries in the .NET framework, where you have to have a certain privilege to use the file system. As an example, is these privilege boundaries, and they're just represented as a dashed line. So obviously not strictly data flow diagram, but just something that we added because it's relevant information that shows where a privilege boundary is being crossed. So for example, if you have an application that does, writing an application under NT that does impersonation, you can say, okay, well everything that executes on this side of the privilege boundary is impersonated, and then it reverts and goes back to the lower trust level or to the lower privilege level. So data flow diagrams we use to better understand the system. It's basically a way of breaking down the system to get a better understanding, a pictorial understanding of how it works. The guidance, and again, you'll hear a little bit different view on it from Mike, but the guidance that I always give is that when you're conducting a threat model meeting, typically you'll end up drawing a bunch of pictures on the board to describe how it works. If those diagrams were relevant in the meeting, presumably they're going to be relevant to somebody reading the threat model later on. So all that sort of information should be captured. So finally, we're going to get to identifying threats. So at this point, what we've described is we've described all the entry points into the system. We've described how the system is intended to be used and not intended to be used. We've described the trust level, so we've described what people are interacting with the system, so what we can tell about them. We've defined the assets that the system has, so the targets that the adversary is going to try and access in some manner. From here, what we want to do is we want to create hypotheses as to, based on these entry points and these assets for the system, what might an attacker try and do. And again, like I said, threats are not vulnerabilities. Threats are things that an attacker just wants to do. So for an example, the file system base class libraries in the .NET framework. If you're talking about a partial trust scenario where the code that's running has been downloaded via IE and it's coming from some arbitrary source, the asset for the file system base class libraries are the actual files on disk, because presumably you do not want some arbitrary code that's running in IE from some untrusted source to be able to open up and read and write to your files, right? So the threat here is that the threat for those file class libraries is that an adversary an example of a threat at least would be that an adversary may try to open up a file on the file system. That does not imply that there's a vulnerability associated with that. That is simply a hypothesis as to what an adversary might do. Obviously, we have mitigation against that. In order to open up a file using the file class libraries, you have to have file I/O permission. So you can see that so that based on this threat, arbitrary user trying to access files, we have some mitigation in place. Well, it requires this permission, and in theory, barring any coding errors that obviously a threat model would certainly cover, but at a high level, barring any other issues, there's no vulnerability associated with that. So that's really the difference between threats and vulnerabilities. Threats is just a hypothesis. This is what an attacker is trying to do, and we have mitigation in place to prevent that from happening. If we don't have mitigation in place for that to prevent that from happening, then it's manifested as a vulnerability. And one of the things that I'll cover when we get down to threat trees is that you can have multiple vulnerabilities for a single threat. One of the things that threat trees or attack trees allows you to do is it allows you to show all the preconditions that have to occur for a threat to be realized, and they're actually pretty good. Actually, it's pretty relevant to what we're talking about, so I'm going to hop ahead, but we'll go back. So the thing about threat trees is that, like I said, you can have multiple vulnerabilities for any one threat. A threat tree at the root node right there is your threat. What some adversary is trying to do. Child nodes are preconditions that have to be true in order for that threat to be a vulnerability. So the way to determine, if you're using threat trees as an analysis tool, the way to determine if there is a vulnerability associated with the threat is you start at a leaf node and you traverse up the tree to the root threat. If you get all the way up to the root threat without hitting a mitigated condition, something that we're protected against, then there is a valid attack path. That valid attack path is the vulnerability. Because there may be multiple, threat attack trees, you can have ANDed conditions, or the default, you can have the ORed conditions. There may be multiple paths from any given leaf node all the way up to the root threat. So based on that, it is possible to have multiple vulnerabilities for a single threat. Threat trees, again, are really just a way of analyzing the threat and seeing how an adversary might actually realize it. So that's another distinction between threats and vulnerabilities. You can't have multiple threats because you can't have multiple vulnerabilities for a threat because a vulnerability is a specific manifestation of that threat. So one of the things that we like to do at the threat level is describe what, in a broad categorical sense, we want to describe what the effect of realizing that threat would be. And this is one of the places that STRIDE comes into play. STRIDE is used to classify the effect of threats. If I can do this, I can cause a denial of service. Or if I could do this, I could elevate my privileges to the ability to run local code on the system. So STRIDE helps us in a number of different ways, not only from just understanding what the threat really is, to also helping us understand risk and other things like that. But this is one of the places that STRIDE comes into play. So threats for the phone. So a lot of you probably have answering machine telephones, and you can dial up, and after it picks up, if you hit 9, then you can enter in a passcode, and then get into your message store. You can maybe change phone configuration, things like that. That's basically the idea with this Fabricam phone. It has some administration interface that if you dial up to it, you can access your messages remotely. You could access configuration remotely. So a threat against this would be that an adversary gains access to that remote administration interface. Notice that I'm not saying how they would do it. The threat is at a higher level than the vulnerability. It's simply to say this is a goal of the attacker. The attacker wants to get access to your administration interface. And we analyze that later on, either using an investigation like a code review, or maybe we use penetration testing techniques, or we use the threat tree. We have various mechanisms for investigating threats, but at a high level, we're just trying to describe what an adversary might try to do. Other things, the adversary wants to read the speed dial list. Maybe they want to make a long-distance call when local access control is enabled. So threats, again, like I said, they describe the entire threat profile for an application. They basically describe all the security considerations that went into the design and implementation of the system. So these are all the threats that we considered when we were designing and writing the application. And in theory, we should be mitigated. That is not always the case, especially when the threat modeling process is not applied at design time. So if you do the threat modeling, if you start threat modeling after it's been designed, after it's been partially or fully implemented, then a lot of times you're going to miss threats that'll have to be fixed, or that'll manifest themselves in vulnerabilities and have to be fixed. So again, like I said, if there are insufficient or no mitigating factors for a threat, then that threat manifests itself as a vulnerability. Again, the reason why another reason that we make the distinction between threats and vulnerabilities is that we're trying to get to a point at some, in the future where we can give this quantifiable aspect to threat modeling to say that we've thoroughly described the attack surface, the threat. Pardon me, the threat profile, and we're mitigated against 90% of them, versus the last milestone when we did threat modeling, we were mitigated against 80% of the threats that we came up with. So we can see that we're doing a better job, as an example. They also help us when we're doing postmortem analysis. So like when a vulnerability is reported in the wild, we can go back and we can say, number one, did we have a corresponding threat? If we didn't, then we need to figure out what went wrong in our process or an enumeration of threats. Did we miss an asset? What did we miss that kept us from enumerating a threat? If we do have a threat, then we go back and look at our analysis. What went wrong in the analysis? Did we miss a potential attack vector in the threat tree? What went wrong? So we don't want to just enumerate the things that are wrong with the system. We want to enumerate all the things that an attacker might try to do, because this really translates into the security design for the system.
Mm-hmm. Are you going to talk about later whether you have enough experience to go back and see how well you've done?
So I just conducted a short threat model review of some threat models that were done in the would-be M2 milestone for the developer division. And
so that was a year ago or 6 months ago? Or?
No,
when did they do their threat model?
The threat models we reviewed were for both M1 and M2. We finished it. We did it at the end of M2. So the threat models were, the oldest ones were probably about almost a year old at this point. So they covered. They actually covered a range of methodologies, because we're obviously, one of the reasons why we're presenting threat modeling now to you is that we're trying to improve our process. And so we've been improving it over the past year, and we hope to improve it further. So the threat models that we reviewed had varying degrees of correspondence to this methodology. And one of the things that we found is that some groups were very good at applying this methodology. They started the threat modeling process early, which is something that we advocate. Again, like I said, because a lot of the information is relevant at design time. Obviously, if you can fix or if you can mitigate against threats at design and implementation time, it costs less. So we found that some groups were able to really apply this quite well, and those were typically the groups that were very schedule oriented. They scheduled definitive time or definite times to do the threat model for the system and things like that, and they tracked their threats appropriately, did appropriate investigation for those threats, and we did find that they had some quite a good success as far as finding vulnerabilities that they probably wouldn't have found otherwise if they didn't do the analysis during the milestone. We found other groups that one of our problems is always is that we're a very large company, and the methodology sometimes is difficult to disseminate. So you see that the groups that had fewer people that went through threat modeling training had a little bit more difficult time figuring out what threats were applicable to their system and things like that. So
was that analysis driven by vulnerabilities found in the field, that you saw weaknesses and you went back and looked, and the ones who did follow the methodology well didn't have them, and those who did have them were the ones who didn't follow them?
Mostly the review that I conducted was more from a process improvement standpoint and not so much driven by any external vulnerabilities.
Oh, how does, in your view, how good a job do people do internally as opposed to what happened to those products?
I think that for our new products for the new products that are going through this methodology, I think we're definitely improving, and I think that we're finding a lot of things before they go out the door that would have otherwise bit us. So I think that the process is working. We have to make it. We have to make trade-offs all the time, as far as amount of time spent on threat modeling versus coding and things like that. And that's one of the reasons why we're trying to make the methodology a little bit more formalized, but at the same time not so formalized that it's it's just check boxes and things like that. So that's part of the reason behind the methodology, is to really bound the discussions and try and encapsulate it into just the relevant information.
I should add just a couple of things. First of all, I assume you're aware of the changes that we made to Internet Explorer in Windows Server 2003, where basically we removed by default all mobile code functionality, and that was derived purely from the threat models. During the security audit for Windows Server 2003, we went back to the IE guys and we said, go revisit your threat models and think about one scenario, just one scenario, and that is an admin browsing the internet from a domain controller. What are the threats? And because of the threats, I'm not talking bugs or vulnerabilities, I'm just talking avenues of attack and potential for damage on that machine. The decision was made, even though it was really late in the game, to turn off VBScript, JavaScript, ActiveX controls, Java applets, and .NET Framework components by default, based purely on the threat model. So that, to me, is just one of the first big, shiny examples of a decision that was made purely on a threat model. No bugs were not a bug. There's no bug being fixed. It was just reducing its attack surface. And the other one is, you may have heard of, there was a big brouhaha recently in the press about some guys in Switzerland who had a whole bunch of hashes where you could do a lookup, and it would give you the password based on a hash. The actual threat model for the SAM reflects that threat, which is if an admin has access, this is an admin threat, if an admin has access to those hashes, which an admin does, and you have weak passwords, i.e. alphanumeric only, then there is the potential for a very fast lookup of passwords. And the belief was that, well, you've got to be an admin to do it, this doesn't apply to Active Directory, and you have to have weak passwords. And so we were having to look at that threat, believing that the risk was actually very low. So we actually have seen things appear that have actually been identified in threat models.
Well, what happens to the models later on, like if you're putting out a patch or testing, did they happen the same pretty well?
So that's one of the things that we're working on. In a lot of cases, that's obviously a concern, right? And we've identified that, and we're trying to improve that moving forward. A lot of times, as far as the developer division is concerned, because I have the most relevant experience with that, or recent experience with them, they do a lot of their threat models on a milestone basis, and so if the feature is changed or the product is changed between milestones, then the threat model is updated to reflect those changes. So we are getting better at that moving forward, but that is definitely a concern. Obviously we don't want the code to be out of sync with the threat model because we're going to miss things.
Is it sort of a requirement that the model is up to date?
Yes. Yeah, that is actually this milestone exit criteria is updating threat models.
And it's the same with Longhorn as well. The threat modeling process is underway. Just going to start now for Longhorn.
So suppose that you got a system right, and there is absolutely no flaw. It's an ideal system. For that, the threat model would be empty, right?
No, not at all.
Vulnerability model. Threats would be.
The vulnerability table may be empty, but the threat table is almost never empty. Right, exactly.
Sorry, I'd like to go back to the question over there about updates. So suppose you have two systems A and B, and you have thread models for both of them. System A doesn't change, but depends on System B, which does change. How do you track all of that?
Yeah, that's another concern that we've identified, especially like I said, one of the things that I pointed out is the systems are interconnected, and if you have these dependencies that break because one system has changed and the other one hasn't, then it invalidates the other system's threat model, right? So that is a concern, and that's something that we're working on. One of the things that one of the potential ways of fixing that is having a database-centric store for threat models, where you can actually assign these dependencies between threat models and have it automatically go and say, hey, this dependency is no longer true. But we're not there yet.
It sounds like potentially you have a management problem there, in that Group B cannot ship until Group A has had time to revise the threat model, right? And
that it is a management problem. And again, like I said, I don't know that we really have that figured out right now.
I should point out that we do have. There's been a huge effort for a bunch of reasons for the main Windows code base to get this dependency database that now exists. And so there's the informal processes of make sure when you're changing things, make sure to flag to the people who are depending on you for any reason that they need to be revisiting their threat models. But it really is at that informal level.
That's a different question. I mean, way back at the beginning of your talk, you were talking about identifying dependencies. Now, during the faculty summit, there was a talk, I think by Marne, about tools which identify dependencies in.
Right, and so that was actually, I'm John Pincus from PPRC. I'm in the same group as Marne, and so that's the database that I was talking about.
Okay, and there are links there.
We actually, believe it or not, we actually talk to each other.
Okay, well, just checking.
Right. I mean, but again, at this point, the links are not yet programmatic, and one of the things I've been working with Frank on is how do we tie into that? Another thing I work on is static analysis. How do we tie the static analysis tools to the output of the threat modeling in two ways? One, can we validate or at least find places where the threat model is out of sync with the code? Two, how do we use this information and use it to be checking some of it statically, to be flagging the things that we can't check statically, and make sure that testing is focusing on those? So these are all areas where work is happening.
Yeah. I guess the other thing is, from a more purist point of view, it seems a bit backwards to be identifying your dependencies programmatically on the code as it exists, and indeed to be identifying them at the threat modeling stage and not at an architectural stage. But I guess that's going back to the point that you made.
My earlier comments.
I think that's a completely fair statement, and the amount of effort that has had to go into this process. The Windows group has been working on this dependency analysis stuff for several years in conjunction with PRC and other groups around research. This is testimony to the fact that the purist approach actually is right. It would have been much better if all of this had been identified up front. And increasingly, that does happen for new code. We have this minor issue of 50 million lines of legacy code, and so there's a lot of these problems. There's this fragility issue that with partial knowledge. So just getting the new information for the new code. That's all well and good, but it doesn't solve the overall problem because all the new code relates to the old code in some way. So we need to get this overall set of information there.
Is there a way of then recording this the next time you need it, or are you going to have to go?
Yes. So in fact, now what's happening, and this is now enforced in both the Windows build and starting in the next few weeks in the CLR work build. The dependencies are now documented as part of each component's build instruction, and these are enforced both for static checking tools. There's a runtime testing harness that finds situations where these dependency boundaries are crossed. So the idea is not to create the same problem in the future.
So I think question over there.
There are several kinds of hidden dependencies. I'm just curious if you have taken them into account. I don't need an explanation of how, if you have. But one of them is correctness. for instance, correctness of generated code out of the compiler, or correct operation of the machine, or peripherals, which ties into asynchrony, timing of operations, things that may block that you don't expect to, such as opening a file or a network connection. And there are certain random events that may be involved. You may have some statistical processes that operate based on probability, back off of network algorithms, for instance. Are those kinds of underlying dependencies taken into account?
Yes. In my experience, we certainly take care of, or we certainly take into account a lot of those. It's difficult to say if we take into account all of them, but a lot of them I know that we do. For example, in the framework, we have a dependency that that the compiler produces correct code, right? So when we JIT compile some assembly that is downloaded off the internet, we have a dependency that is done correctly, such that somebody couldn't attack the system at an IL level and generate these bad native instructions that could allow them to execute arbitrary code. So it's something that we try and take into consideration. Again, it's difficult. That's, I think, a little bit difficult to ensure that we've covered all of them. But I think that we're relatively creative in general. But at the same time, since we also own the compiler, some of those issues are dealt with in the threat model for the compiler itself. So,
as an example, just for you to think about, if it turns out that the next batch of Intel's chips or AMD's chips have a timing problem that an instruction fails, can you go back into the system and identify all the places in software that you may have a problem?
Right. Yeah, and there actually have been, in some threat modeling discussions, there have been, as an example, processor-specific behaviors that have come up that have caused issues. So yeah, I mean, you can't do threat modeling in a vacuum if you have relevant information about underlying systems, or if it becomes available, then you have to apply that.
I mean, by the same token, I'd say that most threat models don't actually go down to the level of detail about which specific machine instructions they're depending on. Right. And so there's a few cases where people are doing they'd be doing it for correctness reasons, not even threat modeling reasons, where people are doing extraordinarily machine-dependent assembly code, where that would be explicitly recorded. In general, though, there would be a higher level dependence on correct functioning of chip that applies to every component. And so I don't know if we'd be able to pull the answer to that specific question out.
Well, you seem to be implying that you depend quite heavily on your compilers in this area. Is it?
We all do. Well, it's
possible. Hold on a second. Is it possible that people generate arbitrary instruction sequences which your processor executes without using your compilers?
You mean in the case of the .NET framework, or
what about what about the threats that appear because of that?
Sure. So somebody puts in some bogus IL instruction or something like that, or tries to, and in some manner tries to generate instructions that are not verifiable. Right. I mean, that's a threat. Yes.
Okay,
and that's
so you looked at all that.
Yes. Yes. And in fact, as far as the .NET framework is concerned, we've got a published ECMA spec for what's verifiable, what's not verifiable, and the instruction set the IL instruction set is very well contained. So we have public information as to verifiability as far as the instructions are concerned. But at the threat model level, it is something that we take into account, that somebody's going to try and attack it at that level. Sure. And that's, again, like I said, because we own the compiler, or the JIT compiler, and so there is a threat model for the JIT compiler.
What does it have to do with the ownership of the compiler?
Well, I mean, if we so as an example, I'm a third-party vendor, and if you're a third-party vendor and you aren't writing the compiler yourself, then you're gonna have a dependency on somebody else who's writing the compiler, right? Does that make sense? I'm just saying that we have a threat model, so that is something that we've taken in.
So specifically, it means that for code that we are writing and compiling and providing, that we can use the compiler as a way of mitigating certain threats. For code,
is there some way that verifies that everybody's using the right version of the compiler?
I heard exactly the same story of borrowers in the mid-70s, early mid-70s, when the entire security of borrower systems was dependent on their compilers.
No, I'm not saying that security is only dependent on the compilers. The security is dependent on a lot of other things.
So I'm a bit sensitive to that because my experience with those systems at the time was that even with the high-level languages they provided at the time, it would generate arbitrary instruction sequences, which completely went around any security because they depended exclusively on the compilers. So I understand your point that you're not dependent exclusively on compilers. I got that. The point is, what kind of analysis have you done in terms of threat modeling outside reliance on compilers?
No, let me put this in perspective. I would suspect that there's only a handful of threats in the entire system that are mitigated by reliance on compilers. For example, the threat that somebody might be able to insert code on the server side that defeats server-side RPC validation, that's mitigated by the fact that we verify as part of the SHIP which version of the IDL compiler is being used, and other people don't have the ability to insert that code into the process. That would be one of the very few things that can be mitigated by compilers. So I want to keep this in perspective.
So I think that one of the scenario that I'm really picturing here, and this may just be a different scenario than what you're talking about, is you can run .NET code in the browser. You can download code and run it in the browser. That code comes from some arbitrary source, some anonymous source, if you will. So a threat to that system is that somebody provides an assembly that has malformed or not verifiable IL, or has some way, in some manner provided malicious IL in an attempt to exploit when that IL is actually converted into native instructions, to exploit that such that they can generate arbitrary native instructions and escape out of the sandbox. So that in that respect, the compiler and vulnerabilities in the compiler are certainly relevant in that scenario. I'm not saying that that's the only. Again, like I said, I'm not saying that's the only threat. Obviously, there are a ton of other threats when you're talking about code download, but.
Let me take it a step further, because several of us, I think, work in some arenas where the concern of the threat on the inside is not from buggy compilers necessarily, but from someone in the process actually putting something in to the compiler, to the library, to the code that may not be obvious, or may not actually trigger until the first patch is issued to complete the instruction sequence. Is that kind of threat, which is a different kind of insider threat, but it's the same idea that you're depending on what you have.
In other words, depending on, are you talking about more like we depend on our developers to not put backdoors?
Yeah.
Yeah. Well, that's certainly. I mean, that's obviously a concern. I'm not the best person to speak about that, simply because I haven't been here at the company for that long. But
some may be inadvertent, and some may actually be carefully crafted, and that is a threat to be concerned with.
Yes.
I think that's sort of where virtual is.
But I'm not even.
That's not all, but that's part of it.
You could generate arbitrary sequences on your server, I would bet, although I haven't done that, without insiders placing malicious code.
So give me a scenario. Well, I mean, generating arbitrary instructions on a server. That's that could be anything. Like, to be honest with you, that's a really broad topic. Are you talking about yeah? I mean, I need a scenario really to be able to address that.
I thought that we just had scenarios in which a packet that carried instruction was executed on servers.
I think we're all in agreement that that's not an example that the compiler can make.
Are we done now with the example?
Yeah.
Okay, good.
Quick query. This is a constructive process to identify all possible threads. But after, when you find out the threads you missed and you're doing patches and all that, are there any characteristics of those threads which were missed, which helps you guide and go back and say, why were they missed in the first place? What was wrong with the process?
So, yeah, that's something that that's something that we've identified as something that we need to work on more. And that's one of the reasons why we're, like I said, we're going with the approach of threats versus vulnerabilities, so that we can go back and figure out where our process or what we missed. And then by doing that, we can see what the root threat for this new vulnerability is, and then we can go and find, presumably apply that new knowledge to the rest of the system, to other systems that or other applications, and try and find similar vulnerabilities, similar threats to other systems.
The experiences so far that you could expand on?
So a lot of the we don't have as far as this methodology is concerned. It hasn't been applied to very many shipping products at this point. So we don't necessarily have a high degree of experience specific to this methodology. As far as products that have shipped, I can say that we do. Anytime an issue comes through MSRC, we do quite a bit of due diligence, not only to analyze it for that. For that specific manifestation, but we try and go back and analyze what the root cause was, and scour the different code bases looking for similar vulnerabilities. So we have a process in place for dealing with that and trying to apply it elsewhere. As far as specifics to this methodology, again, like I said, it's a little bit too new, I think, to apply that. Okay. I am really about out of time. The rest of the talk really is just describing some of the scheduling, how we schedule threat models and things like that, and how we do mitigation, or sorry, how we address vulnerabilities when they're found. And Mike Howe is actually gives a much better talk about how what we do as far as mitigation is concerned, or fixing vulnerabilities is concerned. So I think at this point, if anybody has any questions, I'd like to go ahead and field them now.
So about the schedule then, at what point do you do the threat modeling, and are there, do you do it differently for legacy apps than clean sheet development?
Right. So we've done a little bit of experimentation as far as that's concerned. Again, like I said, certain teams in the developer division had a very rigorous schedule as far as you start the threat model at this point, and it's the responsibility of the designer up until this point, where it then transitions to the implementer and things like that.
When you say designer and implementer, I'm not familiar with those terms of Microsoft. Okay. Program managers and designers,
right?
And the SDEs.
Typically, yes. So there are some groups that have applied a very they have all these different steps on their schedule for a particular milestone. There are others that have kind of gone with a little bit more free-formed application of the methodology. And I think we found what works is if it is built into the schedule, like the first group. And it is started at the beginning of the milestone when whatever the feature or the product is being designed. It works a lot better that way, and we have less things that we have to fix later on. We do good examples of that are things like SQL CLR integration. We started the threat model late, and the threat model actually brought up a bunch of fundamental issues between SQL and the CLR that needed to be addressed. But as far as this integration, it had already begun. It had already gotten to a certain point, and there was a lot of work that had to be done to go back and fix a lot of the issues that were found. So obviously, if we had applied the methodology earlier, I think we would have found a lot of these things, and they would have not been an issue at that late in the game. So.
And legacy versus new.
Legacy versus new. So. A good example of this is actually again in the .NET framework. We are saying that by the time Woodby ships, we would like to have threat models for every feature and every feature in the framework. Now the framework obviously is very old. I mean, obviously it existed a long time before it was publicly available because it was being designed and implemented. So the roots of it were before, well before Michael Howard started giving talks on threat modeling. So there are features that do not necessarily have threat models applied to them. So the idea is that we will go back and we will do threat models for all of these features before before Woodby ships. That's a lot of work, to be honest with you. So not being in the developer division anymore, I'm not exactly sure what the schedule is, but I know that they've committed to that. So the problem with these legacy applications is that when you go back and do threat models for them, a lot of times people have left the group, they've left Microsoft. So it is in some cases difficult to get the knowledge, the requisite knowledge. So you have to do your best.
Designers or the developers have left. Is that what you're saying?
In some cases, there's a lot of cases they've just moved to other groups. So they haven't worked on the code base in a number of years. So they're less familiar with the intricacies of it. So going back and doing legacy applications, very difficult to do. And to be honest with you, I don't think that you can apply the methodology to as good a degree of success as you can with new applications. It's certainly something that you can go back and do, and in fact, we've had cases where externally reported vulnerabilities in legacy applications have driven us to do a threat model for those applications. But typically, you won't see them exist. The threat model exist at a feature level. You'll see the threat model exist at an application level. So it'll be very scenario driven. Right.
Now, the product groups are doing their own threat modeling, right?
Yes.
So when you do a review, you're in the SBU, right?
Yes.
Okay. So when you do a review as part of the SBU activities at the end, are you delivered the threat models so that you all have? Are they reviewed as part of the review?
So there are different levels of review that we conduct. When we're doing, as far as the team that I'm currently on, when we do a security review of a product, then we do go and read and go through each one of the threat models for that product. Again, like I said, I conducted the M2 review for the developer division, which was more of, again, like I said, a process-related review. And then we also have, a lot of teams have peer review. So the threat model that some feature team creates will be reviewed by different people on a different feature team. So we do have some certain review processes in place. Hopefully in the future we'll move to a little bit more of a sign-off sort of criteria. So that somebody is responsible for signing off when the threat model is complete and it has been reviewed, so that we've got a little bit more formalization in it.
So, for example, for the Windows Server audit last year, one of the sign-off requirements was reviewing some of the critical threat models, some of the critical components. Critical being prior history of vulnerability, hanging up on a socket on the internet, unauthenticated connections, those kinds of things. That was absolutely part of the sign-off requirement. So for the big products, the tier 1 products, Windows, Office, SQL Server, Exchange, Visual Studio, and so on, part of the sign-off requirement is a review of the threat models.
Is there a plan to make these threat models part of your source repository so that they're under source control, they have an owner, or are these just PowerPoint diagrams?
most of them are checked into Source Depot or something like that, or under some form of SharePoint portal service thing.
Okay. Yeah. So they're part of the source control process.
They should be. I mean, that's what we tell people to do. Yeah. So in the case of Windows, yes.
Can I just get an idea about new code versus legacy? I just kind of naively assumed that almost everything was legacy and new code is rare. Is that the wrong?
Well, an example of that is IS6 was the core IS6. I'm not talking about like front page extensions or anything like that. The IS6 was a complete redesign and reimplementation, with very little carry.
Every 4 or 5 years, the legacy code will get completely rewritten. Is that kind of what I should think?
It depends on the product. So IS6 is an example where where the previous code base was a lot of it was significantly changed, and it was essentially a new product. Visual Studio and other products like that are continuously evolving, and so for products like that, it's an issue for us because we're always adding new features, and obviously we want to be proactive with those features and do threat models as they're coming online. But at the same time, we're relying on a lot of this legacy code base.
With the context of my question, kind of as an advisory group or researchers or something, is legacy what do you think of the hypothesis is legacy code is always going to be a problem, and we may need a different approach to tackling legacy code than this, what you developed might work really well with new code? Is that, what do you think of that? Or another hypothesis, over time, all that code's going to get replaced, and, we'll have a couple of rough years, but eventually it'll all be new code, so things will be rosy.
So
the old legacy code.
Well, but it'll have gone through this process. It'll be developed in this world versus in the old world. I see two hypotheses here.
Yeah, I mean, the ideal case is that we can't go back and change history, obviously, but the ideal case is that all new code, all new applications are going to use a threat modeling methodology or form of it, and so we'll be in a little bit better. We'll be at a better point 5 years from now than we were previously, because a lot of that legacy code will be active in the product at the same time. At the same time, yes, it's entirely possible that this is not really the right methodology for older code, because it is this methodology works best when you can apply it at both spec time and implementation time. You do it after the fact, that you're doing it at a much higher level. So it's entirely possible that this is not really the right methodology for legacy code.
Maybe somebody who's been here longer would have a perspective on the.
So I can tell what I can tell you is that I used to work for a company called AtStake previous to this, and we applied a very similar methodology when we did different levels we sold different levels of security analysis, and one of them included this sort of analysis for an application that's already built, and we applied it to a relatively good good degree of success. One of the issues there is that since we're coming in after the fact, it's not going to be at as low a level as if we had been there in the first place. So for legacy,
to repair, less expensive to fix, or was that what you mean by low level, or not so deep in the code?
Not that deep in the code. You have to you use the threat modeling to catch more or less the low-hanging fruit, and you have to bolster it with other things like targeted code reviews for critical areas, penetration testing. So if you're doing it against legacy systems, it can't be done alone, really. And so we found that a combination of a process similar to threat modeling as well as penetration testing, we were able to find in general quite a few bugs on every project that we were on. But yeah, it's essentially you're not going to get down to the feature. You're not necessarily going to get down to the feature level in legacy products when you're doing threat modeling, because it just takes a lot more time when you're doing it after the fact. But you can use it at the scenario level relatively effectively.
Can I just point out, Frank has to be somewhere else really urgently. So if we wrap things up, then you can listen to my...
Well, this is actually a good time. We've now got the time scheduled for lunch right now, so maybe we can break for a short period of time, go grab some food, come back and keep the conversation rolling.
Thank Frank.
Thank you. Yeah, definitely.